Today's lesson is entitled Vectors in the Plane. A vector, 2 dimensions, is an ordered pair of real numbers denoted in component form as AB. Notice that it looks like a less than and greater than sign with the AB. It's not a coordinate point on the graph. Standard representation of vector AB is an arrow from the original to the point. The magnitude, absolute value V, is the length of the arrow, and the direction is the direction which the arrow is pointing. A vector 0, 0 called zero vector has zero length and no direction. So vector AB, for example, if I had vector, so it's like an array with a point at the end. If I had vector 3, 4 from 0, 0, that would mean it has coordinates of 0, 0 and 3, 4. It's vector 3, 4, which means it's going 3 units to the right and 4 up. To get to the point. Now, because we're allowed to move it around on a graph, this is the component form, which means any difference of x's is 3, any difference of the y's is 4, and that will still be vector 3, 4. It's the same position as 0, 0, same direction, same magnitude length as the original vector, no matter what we're going to use. So the magnitude is the length of the vector. How to get the magnitude is to take the square root of a squared plus b squared. So my example is vector 3, 4. It looks like absolute value because that's the way we denote it in algebra, but in vector notation it's the square root of 3 squared plus 4 squared, Pythagorean theorem, which makes sense. It's the hypotenuse. And our last picture of the right triangle, so that's square root of 9 plus 16, which is square root of 25, which means that the magnitude equals 5. Direction, we'll do this a little bit later. The direction is basically taking a vector ordered pair divided by the magnitude. So for example, if your vector ordered pair were the vector 3, 4, and the magnitude were 5, 6, 8, doesn't matter what it is. Let's say it's something different than 5. Let's say it's 6. So we then multiply inside the parentheses 3 over 6, 4 over 6, and that would reduce to 1/2, 2/3. We'll talk about direction in terms of an angle a little bit later. This gives you coordinates for direction, not really the angle. The direction angle, which is what we're probably thinking of when we think of direction angle of a non-zero vector is the angle formed by the initial point and terminal point. These are the exact same formulas that we use in polar. It's all based on a circular graphing system. So basically you're just really literally following the formula in degrees, and then if you want to convert it into radians, just remember that you take your degrees, so 30 degrees for example. I want to convert it into radians, so we're going to take and multiply that by 180 over pi to get the radian measurement. So I'll show you that in a little bit. Okay, to get the vector ordered pair, if you just knew 2 points and it's been moved from the original point at 0, 0 on a graph, the math of it is very simple. We're taking and subtracting the x's, so 8 minus 5, subtract the y's, so negative 6, negative 2 minus negative 6, which is always going to be terminal minus initial point, terminal minus initial point. Initial is where we start, terminal is the direction the arrow shows at the end, and it's always in that order. So this would be a vector order pair of, again, so minus a negative plus a positive, so 3, 4. So this shows you a different spot from when we originally started. 0, 0, 3, 4 is another place, but you can move this anywhere you want on the graph. As long as it has the vector order pair of 3, 4, it will work. Okay, if we know the magnitude and direction, we can again go back to some things that we learned in the real brief introduction in polar graphing. This is also based on SOHCAHTOA ratios. X is equal to r cosine theta, y is equal to r sine theta. This is because we know that cosine is x over r, sine is y over r, which is going back to the adjacent over hypotenuse and the opposite over adjacent side. The y over r and x over r being your adjacent opposite sides on a graph. So to find our answer, we put in x equals 3 cosine 30 degrees. And then for y, you plug in 3 sine 30 degrees. This is if you know the direction and magnitude to find our answer. And then plug those in our calculator, and we end up with 2.598 and 1.5. And that's in a vectored order pair. Just doesn't quite fit on my graph thing there. Next. Finding a component form of a vector PQ. Component form again is simply taking and subtracting. Notice the order. So P is the terminal, P is the initial, Q is the terminal point. So it's going to be terminal minus initial. So that would be 1 minus 3. Terminal minus initial, 6 minus 2, so negative 2, 4. And that's my answer. Finding the magnitude and direction. So to get the magnitude, again, we're going to take the square root of x squared plus y squared, which gives us the square root of 16, or 4. And then to get the direction, because we don't know this time magnitude, well, we know the magnitude, but we don't know everything about it, we're going to use the theta equals equation. So formula, when x is negative, is inverse tangent of y over x. So that would be inverse tangent of negative 2 square root of 3 divided by negative 2 plus 180. Find the degree measure first. So this is going to end up being, when you plug this in the calculator, you get 240 degrees. Again, if you want to convert it into radians, so 240 degrees, and we multiply by 180 over pi. So times, or I'm sorry, pi times pi over 180 to get the exact radians. So we did this at the beginning of the year, did the practice from trig class of converting. And then reduce our fraction. So this is divisible by 6 is 4, divisible by 6 here is 3, so 4 pi over 3. Then for the second part, or part 2 here, we're going to find the magnitude, 0 squared plus 4 squared, the square root of 16, which again is 4. When x is 0 and y is positive, theta is always 90. We know that 90 degrees is pi over 2. Vector addition and multiplication. I showed you earlier, multiplying a number inside a vector. You can also add two vector numbers together. We don't usually subtract vectors. We take the opposite of the vector, so we define subtraction by adding the opposite vector. That's just by definition. Some other properties of vectors are distributive property, adding two vectors, positive and negative, getting 0, multiplying by 0 you get 0, multiplying by 1 by vector you get the original vector, and so forth. So you can take a look over all the properties of vectors. They work a lot like coordinate order pairs in a certain sense in terms of solving. Okay, so this is just practice now using the vectors and applying the rules and then getting our answer in terms of the component form and magnitude. So -2 times vector v, so we multiply -2 times vector v, and so that means we multiply inside, so that'll be -4, oops, sorry, +4, so -2 times -2, -2 times 5, -10, component form, that's the component form, magnitude, square root of 4 squared plus -10 squared, so that's square root of 116. And then for u minus v, so we're going to take vector u minus vector v, so 3 minus -2, 5, and then -2 minus 5 is -7. That's our component form, magnitude, square root of 5 squared plus -7 squared, and that would equal square root of 74. If you want to get decimals for these, you can. And then the last one I have on here is -2 vector u plus 5 vector v. So -2 vector u would be -6, comma, 4 plus 5 vector v would be -10, 25. Add those together, we get -16 and 29. There's our component form. Magnitude is square root of -16 squared plus 29 squared, which is the square root of 1097. Okay, drawing vectors is next. I think from what I have heard from past years for drawing vectors that most students prefer to draw vectors using the triangle method. So how that works, I'll just kind of try to sketch it for you because I can't write real well on my board here that I'm using. Basically it's taking vector u, so I literally have to measure it, look at the angle it makes if you want to pull a line there and get its angles. This is vector u. And then from the end of this, you add on vector v, so vector v. Again, I would actually measure it if I had other tools. And then the answer is right here, vector u plus vector v. That's how you draw a vector. If you're doing a subtraction problem, you just draw the vector v going the opposite direction of what it originally is. That's all there is to drawing a vector. Okay, last thing we have are some rules for vectors in terms of a velocity acceleration type of problem, and some things we're going to use it for. So this is more of the calculus part of the problems. The others was more of just a review of vectors. So this is talking about getting a vector and figuring out 400 degrees and, 400 miles per hour encounters a 50-degree tailwind in a direction 60 degrees north of east. Because of the wind, acquires a new ground speed and direction. What are they? So we let u be the velocity of the plane in still air, and v is the velocity of the tailwind. Then vector u is 400, and vector v, absolute value or magnitude, is 50. And that's our speed. So we know absolute value or magnitude is equivalent to speed in a velocity problem. To get our answers, we take vector u, then component form would be 400, 0. Vector v, we'd have to figure out 50 cosine 60, 50 sine is 60. The 400 miles per hour is in still air originally. So we add the two vectors together. So we get our 400 plus the 25. That's the 50 cosine 60. And then 50 sine 60 is the 25 square root of 3. That's our answer. So speed of the two added together, we just do square root of vector u plus v, so 425. That's our first answer. Okay, so that's this answer here. We take that and square it. Take this answer and square it under square root sign. That gives us our speed. And then direction, we just use inverse tangent of, in this case, it'll be inverse tangent of y over x, so that's 25 square root of 3 over 425, and that's our answer for the direction. So here are some general things to look at when doing an acceleration velocity problem. So particle motion. This will be the BC part of particle motion, which is the position, velocity, speed, acceleration, all those fun things that you find in other problems of particle motion. The position vector is your r of t. The velocity is v of t, which is the derivative. Velocity is the derivative of position as a review. So that will be dx dt over dy, and then comma dy dt. The speed is the magnitude. Okay, so that's the same thing as magnitude. Acceleration is the derivative of the velocity, or the second derivative of the particle's position. And then direction of motion, I already went over this one, is taking vector v over its magnitude. Displacement and distance are the other things we'll look at with particle motion. So that goes to the antiderivative or integration portion of the velocity questions. So to get the displacement, you're going to integrate the velocity of each of the values, and then they'll give you it as a ordered pair typically. And then distance traveled is another biggie. So to find the distance traveled, we know the formula for distance traveled is the absolute value of velocity, or the speed of the, so this is the general formula we learn, integral from a to b, absolute value v of t. What we know in this instance is that this is magnitude, and magnitude is the speed, and so the magnitude, so basically you're looking at speed over over time, how far you've went according to how fast you're driving. If you're thinking about a driving problem, for example, or the particle moving. So it's the square root of v1 of t squared plus v2 of t squared. Hopefully you can read yours better on your sheet than I can show on here. That's it for the notes. The examples and problems that you'll work through the next 2 days, we'll take a look at figuring out some of these different ideas. It'll be a good review for the particle motion problems in terms of velocity, just a little different twist on them. And that's it for our lesson for today.